Hello everyone, welcome back to the Fundamental Theorem. In this video, I want to talk about logic. Now, the thing about logic is, without logic, there's no math, right? If you want to know math, if you want to learn more about math, you have to know the basics at least of logic. And not just math. If you want to go into something like computer science, if you want to go into any natural science, if you want to go into philosophy, if you want to go into pretty much anything, you need to have an understanding of logic. Now, here's the thing, logic is something that we all pretty much understand on some level or the other, right? We all use expressions like that makes sense. And what does it mean to say that something makes sense? It means that that something appeals to our sense of logic, right? That's why we consider it to have some meaning. That's why we consider that it makes sense on some intuitive level, right? So we do have some understanding of logic, but let's go into it in a bit of a more formal manner. All right, so the way logic is implemented is through logical expressions, right? Logical expressions are the most basic levels at which logic manifests itself. So, what is a logical expression? Well, a logical expression is simply put a condition of some sort. And the thing about conditions is conditions are binary, right? And what does it mean to say that a condition is binary? Well, binary means that there are only two possibilities. In other words, it's either true or false, right? A condition is either satisfied or it's violated. I mean, this makes perfect sense. It's not, let's say I have a condition that the floor is wet. Is it even possible for the floor to be both wet and not wet at the same time? That doesn't even make sense, right? If I say something like that car is blue, right? Is it possible for that car to be both blue and not blue at the same time? That's ridiculous. In other words, conditions, pretty much all conditions, are either satisfied or violated. The binary, right? And conventionally, the idea of something being satisfied or true is represented using the number one, and the idea of something being violated is represented using the number zero. And since ones and zeros are the only language of this kind of what you call Boolean logic, right? That's the reason why you use the binary number system, that is base 2, when dealing with machines and stuff, because it corresponds to a switch either being on or off. Anyway, more about that some other time maybe. But all right, let's just take a look at a condition. All right, let's say we have light bulb. Now, let's say the condition that we're measuring is whether or not this light is on. So, okay, the way we would actually look at this, or at least one interesting way to look at it, is by graphing it. Let's graph two axes, one of which stands for truth and the other of which stands for time. And when you say truth, a 1 represents the value true and a 0 represents the value false. So for this particular graph, again, it could be pretty much any graph, right? For this particular graph, it would imply that the light is on, then off, and then on again, and then off again. And here's the thing, right? It could be pretty much any graph. It need not have this particular configuration, but do note that it's not possible for this graph to take any value other than 0 and 1. So it's not maybe like a sine curve or something like that. That would be continuous. This is what you would call discrete, meaning that there are only two possible values and there's nothing in between. There's no continuum of values, right? Whereas if I said something like a sine curve, well, the range of a sine curve would be all values from -1 to 1. Again, if you're not sure about what I'm talking about, do take a moment to watch my videos about trigonometry. Right? Now, anyway, coming back to the scenario at hand. Well, you could actually rewrite all of this using plain English and words. I mean, often that's a lot simpler, right? So let's say if the light is on, then it glows yellow. Whereas if the light is off, then it doesn't glow. Okay. So what we've done is we've just split the possibilities that we saw into these two distinct scenarios, right? And again, over here, as we can see, it's only possible for the condition to be satisfied or violated. Now, if you want to look at whether or not these conditions have been satisfied in terms of our truth values, you can see on the axes as well, we will be able to see that the first statement, that is, if the light is on, then it glows yellow, corresponds to a truth value of 1, whereas the second statement, if the light is off, then it does not glow, corresponds to a truth value of 0. So obviously, in this case, you can see the light bulb is pretty much gray, it's not glowing. So it would mean that the truth value for this configuration on the screen right now is 0. Now, notice how these two statements, right? If the light is on, then it glows yellow, and if the light is off, then it does not glow. Notice how they both have this sort of structure. There is a proposition, and then something that you draw from that proposition, right? In other words, there is a condition of the light being on, and then there's some consequence of that condition. So these kinds of statements are what you would call propositional statements. And another word, a more fancy word for that, is the term hypothesis. Now, this concept of a hypothesis is actually quintessential to the scientific method. And before any experiment is performed, usually researchers sort of give their hypothesis, what they believe to be the logical relationship between the quantities being explored. And then they go on to test this hypothesis, and then they analyze the results and so on. Now, the thing about this particular set of conditions is that there's only one condition, right? There's only one factor that affects the outcome, whether the light glows yellow or whether it does not glow at all. So, how do we move from a simple condition to something a little bit more complex? Well, the key is what you would call logical operators, which serve as probably the most important three operators in all of logical thinking. And the thing about these three guys, and or and not, is that they kind of sort of connect propositional ideas, right? At least and or serve to quite literally just combine two propositional ideas, whereas the not kind of reverses a proposition, which pretty much makes sense because not means negative, right? And well, if you're wondering what the symbols are, like the weird caret kind of symbol, and then the V kind of a thing, and then the weird dash with something jutting out underneath, well, these are just symbols. They don't really mean anything much. It's pretty much just a convention. Yeah. Uh, you will see in some books that set notation is used. In other words, intersections, unions, and complements are used to describe and or and not respectively. And if you want to know more about that, I'm going to be talking about it in my next video, so don't go anywhere. Now, anyway, the way you need to interpret these is just the way you would interpret the plain English words and or and not, right? So if I have condition A and condition B, all that means is in order for the condition A and B to be satisfied, both conditions A and B need to be satisfied, obviously. Likewise, if I want the condition A or B to be satisfied, then either condition A needs to be satisfied or condition B needs to be satisfied. Now, they can both be satisfied. That would still satisfy the condition of A or B. Um, but the idea is simply that they should not both be violated, right? Now, not is pretty straightforward. Like I said, it just negates. So if I want to check if a condition is not satisfied, I need to check all the cases where it's violated. So not is just the idea of reversing stuff. Now, the thing is, logical operators are pretty useful in electronics and computer science. In fact, they are like the most important component, right? and they're actually used in the form of what you call logic gates in what you would call logic circuits, where you deal with digital impulses of ones and zeros, the way we saw for the truth values in the previous cases. But let's not go all the way there. Let's just stick to plain English. Now, speaking of plain English, there are two statements that I would like you guys to take a look at, right? First of all, we have the statement, if your homework is done and if it isn't raining, then you can go to play. Now, this is again a propositional statement, as we saw with the light bulb as well. And there's another propositional statement coming up. If your homework is not done or if it's raining, then you cannot go to play. Now, I want you guys to take a moment to think about what the relationship is between these two statements. So, if you want, do pause the video and think about it for a while and then come back. All right, so I'm going to assume that all of you had some time to think about that. And the thing is, these two statements are saying pretty much the exact same thing. There is no difference in the meaning, right? And why is that so? Well, when you think about it, let's just look at the first statement for a moment. Yeah. Both the conditions that your homework is done and that it isn't raining outside, both of these conditions have to be satisfied in order for you to be able to go to play, right? Which means if any one of them is violated, then obviously they will not both be satisfied, right? Which means you will not be able to go to play because they will not both have been satisfied. And this intuitive relationship, right, whereby by negating both the conditions in an and relationship, you actually end up with an or relationship between the negatives. This is what you would call De Morgan's law, and it can actually be understood again using sets and Venn diagrams. So again, that's all for the next video. Yeah. But just on a very intuitive level, it pretty much makes sense that this should be so. Because in order for the condition that both of them should be true to be rendered untrue, just one of the two conditions that make up that bigger condition needs to be violated. Yeah. Now, all right. Wow, that was a mouthful and a half, but I'm sure you guys understand where I'm coming from. Now, all right, let's look at another set of statements. First, we have the statement, if your homework is done and if it's not raining, then you always go to play. Now, this is an interesting addition. And we have another statement now. If you aren't playing, then either your homework isn't done or it's raining out. All right, so again, you guys know the drill. I do recommend that you pause the video, think about it for a while, and then come back. Right, so I'm going to guess you guys had some time to think about that. Now, again, in terms of what these two statements are saying, they're pretty much saying the same thing, right? Except for one little thing. You know how the thing that you have next to your if is kind of getting flipped with the outcome? That's actually pretty significant because you're essentially reversing the directionality. And what do I mean when I say directionality? Well, the thing is, with any hypothesis or with any propositional statement, you would have a proposition and then a consequence, right? In this case, we see that the proposition and the consequence are getting flipped, but they're not just getting flipped, they're actually getting negated as well as flipped. In fact, from a certain point of view, the only reason why they're being flipped is because they're being negated or vice versa. And the thing is, okay, what does that even mean to say that? Well, the thing is, if your homework were done and if it weren't raining outside, then you would definitely be playing outside, right? But if you're not playing outside, then it implies that one of the two conditions has to have been violated. So, from a very intuitive standpoint, it's like you're going there and you're coming back, right? It's like you're going from a proposition to a consequence, but upon identifying that the consequence is not true, the proposition obviously needs to have been untrue, right? And this is a very interesting relationship. Now, there are several ways in which you could actually rephrase the statement and manipulate it and get several other statements. And I'm just going to go over the ways in which you could do this. So, forget about homework and raining and all of that. Let's just say we have some statement. If A, then B, where A and B are just two conditions. Yeah. So, in your statement, A becomes the condition, A becomes the proposition, and B becomes the consequence of that conditions being true, right? Now, the inverse of that statement would be the new statement: if A is false, then B is false. Likewise, the converse of that statement, if A then B, would be if B, then A, right? In other words, you're just flipping the directionality. And finally, you have the contrapositive. If B is false, then A is false. Now, let's say that our main statement, if A then B, is true. Let's say that that statement is a sound and perfectly valid form of reasoning. Which of the other three then, the inverse, the converse, or the contrapositive, would have to be true? I do suggest that you guys take a moment to pause your video and think about what the answer to that might be. All right. So I'm guessing you guys had some time to think about that. And the answer is, drum roll, the contrapositive. And well, this makes perfect sense because we actually just illustrated this in the previous example, right? We saw the whole idea of the conditions for being able to go out and play being swapped when you negate everything in the sentence. We just saw that. So, from a very intuitive standpoint, it would make sense if you guys picked contrapositive. But here's the thing, right? That statement was just an example where this relationship is true. That's not a logical justification of why this is true. So, you know what? I'm actually going to leave this open to you guys. So, if you guys want to express your opinion in the comments, please go ahead and do that. Why do you think that the contrapositive of a statement will always need to be true, necessarily? Please let me know what you think in the comments. Now, that's pretty much it for this video. Now, in the next video, I'm going to go over sets, right? Then I'm going to go over Venn diagrams, intersections, unions, complements, and finally, I'm going to briefly touch upon probabilities. Yeah, and a little bit of counting. Now, that's it for today. You're watching the Fundamental Theorem. Thank you guys so much for watching this video. I hope you enjoyed it. Please like, subscribe, leave your opinion in the comments below, and see you next time. Bye bye.